All right. Jury duty?
Yeah, I was just about to say. Wait, what?
So Monday the 21st, I have jury duty.
Oh.
So on Sunday the 20th, I don't know if anyone here has done jury duty before in this county, but on Sunday after 5 p.m. or 6 p.m., I can go onto the website to find out if I'm needed the next day. So I won't know until the 20th, the night of the 20th, or evening of the 20th, whether I actually will miss class on Monday or not. If I do have jury duty and I'm not selected for a jury, then that's it. It's that one day. If I am selected for a jury, I've been on one that lasted 2 days. That's the longest one I've been on. But they've been, there's a hit and run and drunk driving, and there was another one where some man was living with a woman and then ended up absconding with her stuff. I guess it's theft. So they have not been lengthy trials, but we'll sort of play it by
Harrison
ear.
just texted me.
What was that?
Harrison just texted me. He said, "Let the class know I'm on the way." He said, "I'm sure everyone is missing my presence."
We are. Yeah, sounds like it. It isn't a costume out here, is it? Right.
He can believe whatever he wants. All right, so we last left off some right hand rule stuff. So let's just do what does this represent?
Whatever this is.
Okay. Magnetic field coming out.
Oh, yeah.
And if I shoot an electron up into it, which way will the electron be deflected?
I don't know. Wait, right hand rule, that's right.
Left. You point in the direction of the electron and curl in the direction of the magnetic field. So it goes to the left. Oh, but it's an electron, so it's the opposite.
You're also using your left hand.
Oh,
Yeah, I made that mistake too.
Because it was throwing me, because
So it's-
your logic was right, then I thought, wait a second, it should be
Right.
going off to the left. You were right the first time, it is going to the
it
left.
is going to the left because it's the opposite of what it would be if it's a proton.
Right,
Okay.
Correct.
For the wrong reason.
correct.
Let's see.
All right, does anyone still need help with which way the electron is going to get deflected?
If you went over it again, I wouldn't complain.
Okay.
Yeah.
All right, so we're doing the gun. We got the electrons moving up. Magnetic field, that's these fingers right here, is coming out. And so the thumb points in the direction of the force. Well, points in the direction of V cross B. But since the electron's negative, it flips it. So it's going that way.
So it would have gone out this way, but it's going, oh yeah.
It would have gone this way. If this had been a proton, it would have gone this way.
So if it's an electron, you can use your left hand to do the same technique to get the right answer.
Correct. And that's fine. And some people will do that, and there was one textbook which actually suggested that. The issue is that if you get to the point where you start to get more comfortable and start getting a feel for it, then there's sort of a double negative that shows up sometimes, where you do the left hand, you go, oh, then I need to flip it, and
Right.
so just,
Pick one. Go ahead.
that's my recommendation, but you do you. All right, so we'll be deflected in that direction.
So the force is going this way. The electron's going, wait, how does it?
All right, so finger in the direction that the particle's going, because the bullet comes out the barrel. The multiple fingers, same direction as the magnetic field. And so thumb points in the direction of the force on a positive particle, but the negative, that Q there is negative, so that flips it that direction.
Oh, okay, I see. So because the magnetic field is coming out this way, I need my fingers to point towards me,
Yes,
and this is going up, okay, and then you flip it, okay.
Right.
I understand.
suppose I've got a whole bunch of electrons all streaming in this way. At some point, if I have enough electrons, I'm really sort of talking about there's a current. So having an electron shoot up like that, I can also think about it as I have some, if there are enough electrons, I have some current flowing the opposite direction. So, which way will the wire be forced?
In the opposite direction of the current, with the current?
Still doing right-hand rule. If I think about it in terms of electrons, if I got a bunch of electrons flowing this way, that's like a current flowing that way.
So if the current's flowing this way, the electrons are still flowing. You've drawn the same thing twice essentially, right?
Yes.
Okay. So would it not still be forced in the same direction? to the
It,
left?
it still will be forced that way. But we now have the situation that, well, we'll manipulate that and show about the direction of the force. So let's do that. Let's do some math with a little bit of hand waving. There is a more complex derivation of this, which is accessible to 152. However, it's sort of a pain in the butt. It's going to flash back to stuff that we have done before, but it's just, this is close enough. So velocity, what is velocity?
Distance over time.
Ooh, that's a better answer.
Going for, what'd you say?
Distance over time. Or no,
Acceleration.
Yeah.
I was gonna say speed with direction, but I feel like that's not really.
Well, it is speed with direction, that is true. Distance over time does
displacement
not
over
work.
time.
Thank you, there we go, much better. Why was distance over time not good?
It's because it doesn't have direction.
There we go. All right, so it's displacement over time. That's the one I was going for. You could do it in terms of acceleration, but again, this is the way I wanted it. Cross V. Now this delta t here, I can just, it's a denominator, I can move it around, I'm multiplying here, so I just pull that one out. It's not like it's really involved in a cross product, because cross products involve vectors. So I'm pulling delta t out, so I got q over delta t times delta x cross b. So this is the charge that's flowing past a particular area in a certain amount of time. What is that?
Oh,
That's
what is that?
the one we just used. That's current.
It is correct. And this delta x, we generally do a slightly different flavor of the variable. Because when you're talking about displacement, you really there's a displacement of a charge here, but we're talking about current, so there's this constant moving. And so L cross B. Now L, I've got a vector symbol over, and so the direction of L though is the direction of the current. So the direction of L is direction of current. Technically, current is not a vector, that's why I'm not putting a vector symbol over the I.
But current has direction. So why is it not a vector? Or we don't have to go there, that just doesn't quite.
It does have a direction, but if I have, say I have a circuit like that, I have current flowing up and it's going to split. There is absolutely no difference really between that situation and that situation. So the direction of the current flowing in a wire, yes, does matter, but the direction of the current in terms of some sort of reference frame is really not particularly important. That's the explanation I've heard. And that, I mean, by the same argument, if you want to say that it has direction, time has a direction also, but also.
Oh, no, that's not. So wait, so what is L, the length of the wire?
Yes. That is in the magnetic field,
The length of the what?
the wire.
Wire.
So let's see if I can draw this potentially better. No, hard to believe. So let's say that I have a magnetic field that I can somehow contain. And again, realistically, it is possible to do this pretty well. Not something I can do, but the people with the right equipment can do it. And I got a wire running through it. This distance here would be the length, because that's the part of the wire that's in the magnetic field. And if I have current flowing this way, well, let's use a right-hand rule, L cross B. We can still do the spin gun. Finger in the direction of the current, in other words, the direction of L. B field out, the force is that way.
Oh, but isn't the current, so the current means if the current's flowing down, electrons are then flowing up,
Right.
right? So if electrons are flowing up, I'll use my left hand. Did you come up with the left?
Yeah.
Okay, I don't know what I did. Never mind. I'm good.
I might have, it's possible I said right, because from my point of view, but I pointed in that direction.
No, I think I was confused, but I got it.
So the wire is forced in that direction.
So the whole wire moves?
It will. Well, it might move. I mean, there are other forces involved in the wire, so if I've got the wire clamped here, it's probably not gonna move a whole lot. But for the demonstration we'll do later, yes, you will see physically that the current carrying metal will move.
Over here you have in the I, like parentheses L cross B,
Yes,
you have an arrow and it says direction of L is equal to the direction of the current.
yes.
Can you explain that, like with the picture? Cause here's L.
So L is the length of that, but the current is flowing down, so that's why the direction of L, this vector L, is that way.
Okay. Are we gonna be able to determine like the direction of the current if L is like positive or negative? Like, is that what dictates direction of the current?
Sorry, I had two interpretations of what you said. Ask it again, please.
I guess I'm asking, how are we gonna know the direction of the current just by looking at L? Like, will it be positive or negative?
Oh, I typically will say the current's flowing in such and such a direction.
Okay,
I'll tell you the direction that it's flowing in.
okay.
So we now have we have current flowing through a wire. And being able to get current flowing through a wire, that's something that's, I guess, Ben Franklin was the one who started setting up the standards. But if we take a look at that, so I have a wire here, and we put it in a magnetic field. Here, let me just simplify it. Magnetic field inside this box. And as the current flows, let's say that the current is flowing down. Now we talk openly the fact that these are electrons moving, but at some point they did not know. Again, Ben Franklin thought of current as some sort of fluid flow, and so thus we use the language of fluids. But we don't know whether really, or did not know, whether this was a proton going this way or an electron going this way. Or probably better wording at the time, something positive flowing that way or something negative flowing that way, since they didn't know about electrons and protons yet. So we talked about that if an electron is flowing up into it and the magnetic field's coming out, the electron would move over here. They would get forced over here, depending upon how fast is it going, where it actually hits. But if a proton is being shot downwards, which way would the proton be forced?
Also to the left?
Yep. So we now have a way of figuring out what is actually moving. Because if it's the electrons that are flowing opposite the direction of current, then this side is going to have a lot more negative charges on it. And this side have more positive charges on it. or fewer negative charges. If the proton is flowing, then this side over here will be more positive. Which means now, if I take a voltmeter, a very sensitive one, and I put them on the sides of the wire, well, if I gain potential going this way, it's electrons moving. If I gain potential going that way, it's some positive charge flowing. This is known as the Hall effect, named after Edwin Hall. Hall effect. And 1870s? I don't know why I can never remember when they figured this out. But this is the point in the 1800s when we finally realized, oh, it's negative charges flowing. And at that point, it was too late. They weren't going to change any of the conventions that they had done already.
So just to clarify, protons don't generally move, right? They just did not know this at the time?
Right. They didn't realize that protons existed yet. Matter of fact, they didn't realize protons existed until 1890s or 19 zeros. Somewhere in that range, somewhere around the turn of that century was when they finally realized that protons existed.
Are there positive charges that move, or for the sake of this class, can we just assume it's always electrons that are moving?
You can assume it's always electrons moving unless I specifically say that I shoot a positive charged particle into a magnetic field.
Cool.
Oh, and sort of got it. I've written this up here. This is the magnetic force right here. If that's not there, that's the electric force. So some textbooks will just go ahead and combine them. If I got an electric field going on and a magnetic field as charged particles moving through it, here's the total force. It's nothing spectacular other than the fact that if I have a charged particle moving, potentially I have two different forces acting on it. Test 1A, test 3, or 4, or however you count them. All right, so at this point, we've covered forces on charges moving through magnetic fields. We haven't really spent much time on the magnetic fields that are created. In fact, I don't think we've done any of that. Have we done magnetic field from a wire?
No.
All right.
We just covered like magnetic field from a moving charge, and that's B. Right, like.
The B of Savart.
What?
You said magnetic field from a moving charge, or the force on a moving charge from a magnetic field? There's
I have like a formula written down for B, and it's like mu sub naught over 4 pi q, and then
Okay.
V cross R over R
That's
cubed.
B of Savart law.
That's what?
B of Savart.
Okay. Okay, yeah, it sounded like gibberish, and you wrote it, and it
Yeah.
still looks like
It
gibberish.
did, yep, it does.
It rhymes with Leo Bizarre.
Is that a person?
2 people, I believe.
Right, okay.
Actually, I think it is 2 people as opposed to someone with a hyphenated name.
So that's what B is.
No, that's not, I don't think that's why it's called,
I
B is
had no
used for
idea.
that.
Are they two Frenchmen?
I would guess so.
That would make sense considering the pronunciation, or it could be just, no, rhyming with Leo Bizarre was something that I read in the book.
Is that like the way you were taught to remember it? Like, remember?
Yeah.
Theo Savar by Leo, okay.
As opposed to, yeah, I think I pronounced the T before I read that bit. The T's, plural. Alright, so this is the generalized formula, and again, it's really difficult to deal with. It's simple enough if I have a single charge, but if I've got a collection of charges, it's a lot more difficult. So I'm gonna put that up again. But what we care about primarily at this point is if I have a current, how do I deal with that? Because the formula with a current, we're dealing with a differential here. And if you're completely unfamiliar with this, it seems like I've probably used this before, but if you're unfamiliar, I'll translate it into 152 in just a second. When you see the D in front of something like this, and if someone calls it a differential, just think of it as a really tiny change. So in a 152 textbook, you're more apt to see delta V is equal to mu naught over 4 pi I delta L cross R over R cubed. They are very, very similar to each other. The only difference really is that delta, generally, it's something that I can measure. What's the change in time, the delta T, whereas this is infinitesimally small. Not zero, just incredibly small. And so this allows for adapting changes for subtle changes. So if I have a current running like this and I want to know the magnetic field it creates at this point, then what I end up doing is, in essence, finding the magnetic field from this point, and then the one next to it, then the one next to it, then the one next to it, and do an infinite sum of infinitesimally small things. That's Calc 2. If you have not had any calculus, then later on when you get to it, you'll go, oh, okay, that's what he was talking about. Because no doubt you will remember this moment.
Never have to take Calc 2, thankfully. So.
Thankfully, yeah.
It's your loss.
Calc 1 was enough.
None for me.
That was
Thank
perfect.
The advantage of Calc 2, when you get into integral calculus, you actually start deriving some of those formulas you'd been using before, like the area of a circle is pi r squared. You can derive it. Area of a sphere, 4/3 pi r cubed, you can derive it. It brings a lot of pieces together that, which for me were just a lot of, hey, here's the shape, here's the formula. Why?
Well, it's super useful, but it's not exciting.
What's that?
I said it's super useful, but it's not exciting.
Not excited.
I'll just take the formula.
It was good for me.
I'll just take the formula.
Yeah, hand waving is great.
Philistines. All right.